Okay, Math 30. Here we go. This is a wonderful chapter. So we start with Joe is shopping for a car. The dealer says that he has 3 different models and that each model is available in 5 different colors. Use the tree diagram to determine how many different choices Joe has. So tree diagrams are really helpful. He's got 3 different choices of the model. So model 1, 2, or 3. If he chooses model 1, he can choose blue, red, purple, white, or black. And then same thing if he chooses model 2, blue, red, purple, white, black. Same for model 3. Then use the tree diagram to determine how many different choices Joe has. Well, they've listed out the choice here. You don't have to write this. This takes way too long. I would not do this whole entire column. So we can see he's got 1 choice here, 2, 3, 4, 5, 5 here, 5 here. So 15 different choices total. Look at the number of choices there are for the model. So 3 different choices for the model. And the number of choices for the color. 5 different choices of the color. And how do you use these numbers to arrive at your answer in A? Well, if we times those together, we're going to get how many different choices that he has. So then it tells you, consider a task made up of several stages. If the number of choices for the first stage is A, the number of choices for the second stage is B, etc., then the number of ways in which the task can be completed is A times B times C. And this is called the fundamental counting principle. So this will free up some time because you don't have to draw the tree diagram. So example 1. A toy manufacturer makes a wooden toy in 3 parts. Part 1, the top part may be colored red, white, blue, or pink. Part 2, the middle, may be orange, purple, or black. And the bottom may be yellow or green. Determine how many different colored toys can be produced using a tree diagram and the fundamental counting principle. This gives you a good double check to do it both ways. And sometimes one way you like better than the other depending. So your choice. A tree diagram. So I'm going to think part 1, I can do red, white, blue, or pink for part 1. Then if I choose red, I still have all these choices for the middle. So part 2, red, I can do orange, purple, or black. Same thing here. Orange, purple, black. Same thing here. Orange, purple, black. And by this time I'm kind of tired of it, but I will keep going. Orange, purple, black. And then the bottom, yellow or green. Thank goodness they only chose 2 different colors for that. So here I could be yellow or green, here, yellow or green, here, yellow or green, etc. I could write the whole thing, but once I get to there, I can see that I've got 4 choices for that part 1. So part 1, I've got 4 choices. Part 2, I've got 3 choices. Part 3, I have 2 choices. I'm using all of those. So I have part 1 and part 2 and part 3, which means I'm going to times those together. And that will give me a total of 24 choices. If I look here, I can see from the red I've got 1, 2, 3, 4, 5, 6 choices because I'm going to have red, orange, yellow for 1, red, orange, green for 1, etc. That 6 is going to be the same thing here for if I chose white first, or blue first, or pink first. And if I add all those guys up, I'm going to get 24. So both ways, I end up with 24. Fundamental counting principle is obviously quicker. And for large diagrams, we don't want to draw. over the page. In the previous example, the toys consisted of part 1 and part 2 and part 3. Total number of possible toys was found by multiplication. In any example involving and, the total number of arrangements will be found by multiplying. You will naturally say those words and just listen to yourself. When you say and, you write down times. So, a math quiz consists of 8 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? So let's draw little lines for our questions. We have 8 multiple choice questions. 1, 2, 3, 4, 5, 6, 7, 8. Each has 4 choices. So question 1 has 4 choices. Question 2 has 4 choices. Question 3 has 4 choices, etc. So if I times those all together, I've got 4 to the 8 choices that I could have. And if I put that on my calculator, I get a nice big number, 6, 5, 5, 3, 6. Different choices, different number of answers that I could get for my test. Okay, number 3. When solving problems involving restrictions, and you're going to get lots of these, it is important that the restriction is dealt with first, as in this example that we're going to do. We will just do it on the side and talk about this as we go instead of using their parts. So Eric has been assigned the task of determining how many odd 4-digit numbers there are. So 4 digits, 1, 2, 3, 4, and they have to be odd. He has been told that a number such as 5,267 is a 4-digit number, whereas 0 to 67 is classified as a 3-digit number. So obviously, if you're 17 years old, you would not write 0017. You would just write the 17, and that would be a 2-digit number. So 3 digits can't have a 0 at the front, and that's what we're going to think of here. Can't have a 0 at the beginning. His first step, blah, 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 complete his work to determine how many 4-digit odd numbers there are. Okay, let's start. 4-digit odds. Okay, we're going to start with the most restricted space, and that is going to be this end spot. To make the number odd, I have got to have an odd number at the end. So if I end in a 7, that's going to make that whole thing odd. So if I ended in a 1, 3, 5, 7, or 9, I would have an odd number. That gives me 1, 2, 3, 4, 5 choices. And let's just say I pick 7. Okay, then we're going to go to our next most restricted space. That'll be this first one. It can't be 0. So I can have anything between 1 and 9 for that. That gives me 9 choices. Let's say I pick the number 2. Then this next space, this has no restrictions. I can pick anything I want there. So I can pick anything between 1 and 10. Oh, I guess not 10. 0 and 9. In between 0 and 9, so I've got 10 choices, and then same for that next space. I don't have any restrictions. I need a first digit, a second digit, and a third digit, and a fourth digit, so and in between all of those, I'm going to multiply those together, and that will give me 4,500. So this number that I chose, if I would have picked something here, what if I pick the number 5, what if I pick the number 2 again? It didn't say I couldn't. So this would be the number that I have picked. 2, 5, 2, 7. Is it 4 digits? Yep. Is it odd? Yep. And I don't really need to choose a number. This is just going to help me. Okay, then B part. Eric has now been assigned of determining how many odd 4-digit numbers there are which have no repeating digits. And this is where choosing is going to come into play. So 1, 2, 3, 4. I'm still going to start with my most restricted space. here at the end, I've got to have 1, 3, 5, 7, or 9. So I've got 5 choices. I'm still going to pick the 7. Then I'm going to go to this first space. It can't be 0, but now it also can't be whatever I picked here. And I picked 7. So it can't be a 7, which means I have 8 choices possible there this time. Okay, going to my next space, I am going to pick that 2 again for the first space. So now here, I can't pick the 7 that I already chose. I can't pick the 2 that I already chose. The 0 is back in because I could choose it for that space. So I've got 8 choices for this space. And now let's say I pick the 5 again. Okay, then I go to my next space. I can't have the 7 that I already picked. I can't have the 2 I already picked. I can't have the 5 I already picked. So I've got 7 other digits that I could choose. And let's say I pick 1. So I need a first digit and second digit and third digit and fourth digit. I'm going to times all of those together, and I get 2,240 different numbers that I could have chosen that would match these requirements. So the number I ended up choosing, the 2517, is it 4 digits? Yes. Is it odd? Yes. No repeaters? Yes. So, hooray for us. Okay, next page. Those are super great ones. Oh yeah, car license plates in an African country consists of a letter other than I or O, followed by 3 digits, the first of which cannot be 0, followed by any 2 letters which are not repeated. How many different car license plates can be produced? Okay, let's draw little lines to help us out. Consists of a letter, so we're going to have a letter other than I or O, so not I or O, probably because those look like 1 and 0, followed by 3 digits, 1, 2, 3, the first of which cannot be 0, followed by any 2 letters which are not repeated. So letter, letter, not repeated. And it's talking about not repeated between these 2 that they choose. It's not referring back to this first one, although that is not super clear. Don't worry, on a test I will make it super clear whether you're including that as part of the non-repeating. How many different car plates can be produced? Okay, now let's fill it in. Letters. In the alphabet, I have 26 letters. I'm not using I or O, so I will have 24 choices there. Digits. I can't use 0, so I'll have 9 choices. Here, I can use 0 and everything else, so I'll have 0 to 9, so 10 choices. Here, no restrictions, so 10 choices. A letter, and again, no restrictions on the letters, so I have 26 letters in the alphabet, and I just can't have the repeater, so I can't have whatever I used in that space before. So let's say I picked M, that means I can't have M here, so I've got 25 choices for that last space. And I'm going to times all those together, and I end up with 1, 4, 0, 4. 1, 2, 3, 4 zeros. A nice big number. Here's a little aside. Vowels in math. There are 5. So A, E, I, O, and U. Math is definite. We're not using any of the sometimes, just the for surezies. Okay, number 5. Here's another way they can use this same thing. Now we're going to go on a little trip. Woohoo! Hope you had your shots. There are 2 routes from Pitland to Queensville, and that's not very exciting. So we're going to go from Paris to Queensland, Australia. 3 routes from Queensland to St. Luke's. That's not even fun. We're going to go to Sydney. And then Pitland to Rutherford, so Paris to Rome, and 1 route from Rome to Sydney. Okay, so here's you on the airline, and this is what they're showing. You can go Paris to Queensland via this route or via this other one. Then same. From Queensland, I could go this route, this straight route, or the loop down here. And same with Paris to Rome, and then Rome to Sydney, there's only 1 flight that goes out of there. So how many routes are there from Pitland, which is Paris, to St. Luke's passing through Queensville? Well, great. Let's just take a look at this diagram and go all the way to Sydney to start with. So from Paris, I can take this route, one route here, 1 route here, 1 route here, 1 route here. So if I go to Queensland, I've got 1 route, I've got 2 routes that I could have taken to get there. From Paris to Rome, 1, 2, 3 different routes that I could have taken. Okay, then this 2 is going to continue along here to go to Sydney. 2 routes that could have come from there, and then straight along here, 2 as well, 2 as well. So now I've got 1, 2, 4, 6 routes total coming into Sydney from this way. Rome, this 3 continues on. And then I've got, going into Sydney total, the 6 plus 3, 9 routes going into Sydney. So that'll be my very end one. Pitland, which is Paris to Sydney. I've got 9 total routes. And if they want me to go part way, how many routes from Pitland to St. Luke's passing through Queensland? So just this. Paris to Australia. So I'm just looking at the 2, 4, 6 added in getting to Australia. Really what's happening is you're just adding whatever is on that line. You're just adding it together. So I've got 6 total. How many routes are there from Pitland, from Paris to St. Luke's, going through Rome? So Paris to Sydney, I've only got 3 routes possible. 3 coming in from there, and then that one just continues on. So in part C, we could travel from Paris to Sydney via Queensland or Paris to Sydney via Rome. The total number of routes was found by adding the answers. In any example involving or, the total number of arrangements will be found by adding. Hooray! So or, you're going to add. Let's do this one, and it will make sense to you why they say that. The telephone numbers allocated to subscribers in a rural area consist of one of the following. Digits 3, 4, 5. So 3, 4, 5. Followed by any 3 further digits. So 1, 2, 3 digits. Or the digit 2 followed by one of the digits 1 to 5 followed by any 3 further digits. How many different telephone numbers are possible? Okay, so has to be a 3 to start with. There's only one choice of that happening. Has to be a 4, one choice of that happening. Has to be a 5, one choice. Then I can choose any digit for the next space. So 10 choices, 0 to 9. Same thing, same thing. For my phone number, I need the 3, 4, 5, and the rest of those. So those will be times. Or is going to be a plus. Then I have to start with a 2. There's only one choice of that. One of the digits, 1 to 5. So 1, 2, 3, 4, 5. I've got 5 different choices. And then followed by 3 further digits. So I have no restrictions on those. 0 to 9 choices for each of them, so 10 choices total. And now these will get multiplied together. So I've got this group as a phone number option, or this group as a phone number option. And if I add those together, then I end up with 6,000 total. Okay, and last example, here we go. Consider the number of distinguishable 4-letter arrangements that can be formed from the word English. Note, there is an implication that each of the letters in the word English only occurs once and cannot be repeated. So you're going to want to think about that like Scrabble tiles. Look at that. And now let's do this. Just determine the number of distinguishable, which means different, 4-letter arrangements. So we're only going to take 4 that can be formed from the word English if any letter can be in any position. Okay, first let's think. We're only taking 4 letters, and any letter can be in any position. So to start with, for my first letter, I've got 1, 2, 3, 4, 5, 6, 7 choices. And let's say I pick E to go first. Then my second choice, I've got 1, 2, 3, 4, 5, 6 choices. Let's say I pick the L. And this will be a nice little trip for me, England and L, where Lithuania. Then my next letter, I've only got 1, 2, 3, 4, 5 left. And I'm going to go G to go to Greece. And then last, I only have 4 choices. Oh, Nish. That wasn't on purpose. And let's say I'm going to go with the N. Norway is where I'm going to go. Okay, so that is 7 times 6 times 5 times 4 gives me 840 different little arrangements or little words that I could have made out of those starting 7. Okay, let's do the next one. So back all of these go, and I don't have to have them in order. There they are. Okay, now I'm still going to only pick 4 letters, but my first one has to be an E. Well, I only have one E, so one choice. There we go, has to be an E. And then nothing else that has to be for choices. Okay, so let's think. I have 6 choices left for this one. I'm going to pick H and go to Hawaii. And then my next space, I've only got 5 left. And I'm going to pick S and go to Switzerland. And my last ones, I only have 4. And I'm going to go to the Netherlands. There I go on my little vacation in my mind. And that is 120 when I times those together. So 120 different trip options I could have had. The first and last letter must be the vowels. 1, 2, 3, 4. So this has to be a vowel, this has to be a vowel. Let's look. E, N, G, L, I, S, H. So I'm going to arrange them so that I've got the vowels in one column for me to look at and the consonants in the other one. So first and last letters must be a vowel. Well, my first vowel, I can choose one out of those 2, so I've got 2 choices. I'm going to choose the E. My second letter, I can pick one of these 5. I'm going to pick the H. Then I need to pick another consonant, so I'm going to pick the G. Oh, I had 4 choices. And last, I have to pick the remaining vowels, so I only have one choice there. And there is my 4-letter arrangement, or 4-letter little word. And I times those all together, and I end up with 40. For the number of options I could have had for choosing that. Okay, the word must contain G. Okay, here we go. If I think of this, I have 1, 2, 3, 4. Well, if I pick G at the beginning, that contains a G, but what if my G sat in the second spot? Or what if it sat in the third spot? Or what if it sat in the fourth spot? So I've got some OR options going on there, which will mean I'll have to add all of those cases together. So if I pick the G now, that's only one choice. There's only one of them. Then I've got 1, 2, 3, 4, 5, 6 left for my next spot. 5 choices left to choose from for my next one, and 4 left for my last one. And that's going to give me 120 choices if I choose the G at the beginning. But what if I choose something else to start with? What if I do the L first? So I had 7 choices. Oh, I shouldn't do that, because here's what I have to think of. I have to start with my most restricted space. So I have to start with this space number 2, choose the G first. Then I go back to this first space, and I've only got 6 choices. Third space, I've only got 5 choices. And last, I've only got 4. So I'm going to end up with the same number of possibilities happening no matter where I end up putting that letter G. So this will also be 120 choices, this will be 120 choices, and when I add those all up, I'm going to get 480 choices total. Guess I should put a little plus in between there for OR. Okay, isn't that fantastic? That is it. So enjoy your questions, and we'll see you tomorrow.